Hello everybody, Professor Brown here, and this is the Chapter 6 presentation. In Chapter 6, we are going to be looking at the composition of substances and solutions. So we are going to take a look at chemical formulas a little bit more closely and see what they can tell us about what makes up a compound, and then we will define the different parts of a solution and discover how we measure the concentration of solutions, and we will do some examples of those calculations throughout these presentations. One of the ways we measure the mass of a molecule or an atom is with the atomic mass unit. The atomic mass unit is calculated by taking 1/12 of the mass of a carbon-12 atom, and then all other elements' masses are measured relative to this. Because carbon-12 has 6 protons and 6 neutrons, and we take 1/12 of that weight, we can say that protons and neutrons each have an atomic mass unit of about 1. Now that's not exactly right because the electrons do have a little bit of mass, but it's really so negligible that we can just say that protons and neutrons have an atomic mass unit of 1, and then we can find out the mass of an atom by adding up how many protons and neutrons it has. Just for a little bit of information, one atomic mass unit is equal to about 1.6605 times 10 to the negative 24th grams. So we can see from that figure that the atomic mass unit is a very small magnitude. One of the useful things about the atomic mass unit and the way that it was standardized to the carbon-12 atom is that it allows us to determine how much 1 mole of a substance in particular weighs. We will call this figure molecular mass for covalent compounds or unit formula mass for ionic compounds. A lot of times those terms, you may see them used interchangeably. For the covalent compounds, we do see molecular mass quite a bit, but sometimes you'll hear people say molecular mass for the ionic compound formula units as well. And you also may hear these other terms, molecular weight, formula weight, or molar mass, kind of interchangeably. What they all refer to, however, is each tells how many grams 1 mole of that substance weighs. And keep in mind that 1 mole is equal to 6.02 times 10 to the 23rd of any single entity. Usually these figures are reported in G/MOL or G times MOL to the negative 1, and both of those units read the same and mean the same thing, and they tell you grams per how many mole per 1 mole of that substance. So finding this so-called molecular or formula mass is rather trivial for most molecules. All we have to do is look at the formula and determine which elements and how many of each of those elements are present in 1 molecule of the substance, and then add up each of those elements' average atomic mass. So you would look at the periodic table and find the larger number on the entry for that element in the periodic table, which generally represents your atomic mass. And you add all of those atomic masses up together, keeping in mind that if there is more than one of those elements present in the compound indicated by a subscript in that chemical formula, then you would add that element's mass that many times. And then, of course, we have some examples here on this slide. We see for methane, if we want the molecular weight of methane, we look at the formula, and the formula shows us that we have 1 carbon atom in 1 molecule of methane and 4 hydrogen atoms in 1 molecule of methane. And so when I consult a periodic table, I see that Carbon has an atomic mass of 12.011, and that each of the 4 hydrogens all have a mass of 1.008 grams per mole. And so to find the molecular mass of the entire methane CH4 molecule, I would add 12.011 plus 1.008, and I would add the 1.008 4 times to get to a result of 16.043. So 1 molecule of methane weighs 16.043 atomic mass units, and 1 mole of methane has a mass of 16.043 grams. And then we can see the same thing here for our water molecule. In this example, they have rounded the atomic masses from the periodic table off relatively to whole numbers. However, everything still works out pretty much the same. The mass of 1 oxygen is 16, so you can see that they've added 16 plus 1 plus 1 to see that 1 molecule of water has a molecular mass of 18 atomic mass units. And furthermore, 1 mole of water weighs 18 grams. So atomic mass units and grams per mole are interchangeable like that. It's just the only difference is what they're describing. Atomic mass units is describing the mass of 1 individual molecule or atom of an example of that compound, where the grams per mole is telling you how many grams an entire mole weighs. I've got an example here of calculating the molecular weight, the molecular mass, the molar mass of the compound glucose, which is simple sugar. Glucose has the formula C6H12O6. And you can see I shortened this up a little bit by, instead of adding 12 6 different times, I simply multiplied it by 6, and the same for the hydrogens and the oxygens as well. Notice I kept everything in parentheses as I would when I typed it in my calculator, so that the calculators will follow the correct order of operations. In any case, I have 6 carbons and their masses totaled up, and then I have 8 hydrogens with their masses totaled up, and 6 oxygens with their masses totaled up. And if you add all of those together, you get the result of 180.156. And so what this tells us is that 1 molecule of glucose has a mass of 180.156 atomic mass units. And furthermore, 1 mole of glucose has a mass of 180.156 grams. Being able to determine the molecular mass of a chemical formula and then apply that molecular mass in ways to determine what kind of reactions that specific compound would undertake is an important part of doing chemistry. But what if we don't know the chemical formula of the compound we're working with? What if we have an unknown compound and we would like to deduce what that chemical formula is for that compound? We're going to talk about some ways that we can come to that answer specifically in this first couple of sections of Chapter 6. So the question we're going to ask is, how can we find the unknown formula of a compound? We have our first step here, and we can see that step 1 is to determine something called the percent composition. So for the percent composition, what we're trying to do is to break down a compound into its constituent elements and then analyze how much each of that element is present relative to each other. And we can see we have a formula for determining percent composition, and this would be percent composition of a single element in a compound. The way you determine it is you take the mass of that element that is present, and you divide it by the mass of the total compound that is present. And then you multiply that result by 100%. We'll see some examples on the next couple of slides. Our first example reads, 10 grams of an unknown gas is analyzed and found to be composed of 7.5 grams of carbon and 2.5 grams of hydrogen. Calculate the percent compositions of carbon and hydrogen. We start step 1 by setting up the formulas like we saw on the previous slide. The percent of hydrogen will be equal to the mass of hydrogen divided by the total mass of the compound times 100%. And the percent of carbon will be determined by taking the mass of carbon, dividing by the total mass of the compound, and multiplying that by 100%. When we set up our formula for hydrogen, it will look like this. The percent composition of hydrogen is equal to 2.5 grams divided by 10 grams times 100%. And the percent composition of carbon is equal to 7.5 grams divided by 10 grams times 100%. After calculating those results, we find that the percent composition of hydrogen in this particular gas is 25%, and the percent composition for carbon for this particular gas is 75%. Our next example asks, analysis of a 12.04 gram sample of a liquid compound composed of carbon, hydrogen, and nitrogen showed it to contain 7.34 grams of carbon, 1.85 grams of hydrogen, and 2.85 grams of nitrogen. What is the percent composition of this compound? So we're going to determine what the percent compositions of carbon, hydrogen, and nitrogen are in our unknown liquid. To determine the percent composition of carbon, we will take the amount of carbon present and divide it by the total amount of compound and multiply that by 100%. Typing that operation in our calculator gives us a result of about 61%. To calculate the percent composition of hydrogen in our compound, we take the total amount of hydrogen present, 1.85 grams, divide by the total amount of compound, 12.04 grams, and multiply by 100%. Typing that into our calculator, we see that that is approximately 15.4%. Finally, to determine the percent composition of nitrogen in our compound, we will take the total amount of nitrogen present, 2.85 grams, divide by the total amount of compound present, 12.04 grams, and multiply by 100%. Typing that in our calculator, we can see that this results in about 23.7%. So our unknown liquid is composed of about 61% carbon, 15.4% hydrogen, and 23.7% nitrogen. Here on this example, we read, a chemist determines that 1.26 grams of iron reacts with 0.54 grams of oxygen to form rust, otherwise known as iron oxide. What is the percent composition of each element in the new compound? Now, for this example, they are assuming that you will assume that all of the iron gets reacted with all of the oxygen to form our rust. And when that happens, we can assume that the final weight of the resulting compound is the addition of the two elements that make it up. So the total weight of the compound would be 1.26 plus 0.54 for a total of 1.80 grams total of the new compound. And with that information, we can figure out how much the percent compositions of iron and oxygen in our compound are. And so the percent composition of iron would be 1.26 divided by 1.80 times 100%, giving us a total of 70% iron in our compound. And we'll go ahead and calculate the percent composition of oxygen, even though we can probably figure it out pretty quickly from looking at that 70%. We would like to see it mathematically anyway. 0.54 total grams of oxygen divided by 1.80 grams total compound times 100%. Should give us 30, but we'll plug it in our calculator to make sure. And yes, that's exactly what I get, 30% oxygen. Here's our next example. In the lab, a chemist analyzed a sample of methanol and found that it was made of 6.2 grams of carbon, 4.1 grams of hydrogen, and 15.9 grams of oxygen. What is the percent composition of each element? So again, for this one, they're going to want you to assume that all of the amounts of each separate element made it into the compound, and so therefore the total overall mass of the compound is each of the different elements added up, and the total mass in this case would be 6.2 plus 4.1 plus 15.9, which should result in a total mass of about 26.2 grams of total compound. And then to determine the percent composition of each element, we will take each element, starting with carbon. We will put the element's mass, in this case 6.2 grams, divided by the total mass, 26.2 grams. Multiply by 100%, and punching that in our calculator, that results in about 23.7% of our compound. For hydrogen, we see that we have 4.1 grams of hydrogen, and we know that we have 26.2 grams of total compound. Multiply by 100%. We see that we get 15.6% of our compound is hydrogen. And finally, we are going to calculate the percent of oxygen in our compound. We see that we have 15.9 grams of oxygen, 26.2 total grams of compound, multiply by 100%. I'm starting to want to leave that step off a lot. We arrive at about 60.7% of our compound is oxygen. Here we have a little bit of a different example. Sometimes you may be able to determine how many moles of a substance are present without being able to determine directly how many grams of a substance are present. And so this question asks us, a compound contains 1.2 moles of carbon and 3.2 moles of hydrogen. What is the percent composition? Notice it says by mass here in this compound. And because it says by mass, we're going to have to do a few extra calculations. The reason being, moles of carbon and moles of hydrogen have different masses, so therefore we can't directly compare their masses through the molar calculations. So before we do the percent mass determination, we have to figure out what mass of each element we have. And so we may remember that we can do that by multiplying by the atomic mass of each of these elements. And so to determine how many grams 1.2 moles of carbon is, I will write out 1.2 moles of carbon. And then I want to convert that to grams, so I'm going to set up one of my dimensional analysis crosses. And I can see from the periodic table that there is 12.011 grams in 1 mole of carbon. So I can get moles to cancel by having one on top and one on bottom. And I see that the total mathematical operation will be 1.2 times 12.011 divided by 1, which is essentially the same thing as 1.2 times 12.011. So I will type that in my calculator, and I will see that my sample contains about 14.4 grams of carbon. Then I will do the same thing for hydrogen. I see that I have 3.2 moles of hydrogen in my compound. I know that I want to convert it to grams, so I'm going to set up another dimensional analysis cross. And I need to cancel out moles of hydrogen, so I will look on my periodic table and see that there are 1.008 grams of hydrogen in 1 mole of hydrogen. And I put moles on the bottom here because I want to cancel out the moles on the top in the first term. So I will cancel out moles, and I see that the operation I am told to do is essentially 3.2 times 1.008. And that results in about 3.22 grams of hydrogen in our sample. This time we can assume that all of the grams are in the sample, so we can add 14.4 and 3.22. And see that there is approximately 17.62 total grams. And again, that came from adding the 14.4 and the 3.22 of the hydrogen together for a total of 17.62 grams of total compound. Now we can go forward with figuring out percent composition by mass. So for carbon, percent composition of carbon would be 14.4 grams of carbon divided by the total grams of 17.62, multiplying by 100%. We can see that that compound is about 81.7% carbon. And then if we want to figure out the percent of hydrogen, we will do 3.22 total grams of hydrogen divided by 17.62 total grams of compound times 100% for about 18.3% of hydrogen in our compound. So sometimes we are given just the chemical formula and asked to determine the percent composition based on that. One of the good things about the atomic mass unit is that it is a standardized mass, meaning we can essentially treat it like grams when given a formula and asked to find the percent composition. We can see some examples of this on the next couple of slides. So we have our first example of this on this slide. We're asked to determine the relative percent composition of each element in a sample of KClO3. This is an ionic compound known as potassium chlorate. So we can see that one formula unit of potassium chlorate contains one atom of potassium, one atom of chlorine, and 3 atoms of oxygen. We can look at a periodic table and see that an atom of potassium has 39.098 atomic mass units. Chlorine has an atomic mass of 35.45 atomic mass units, and oxygen has an atomic weight of 15.999 atomic mass units. Now, it's important to point out that none of these are grams, they are atomic mass units, but since that is a standardized measure of mass, we can use that to determine relative percent composition. So our total compound would actually have 3 oxygens. So 15.9999 times 3 is going to give us 47.997 total atomic mass units of oxygen in that formula unit. And then if we want to know the total weight of one formula unit of potassium chlorate, we will add the 39.098 plus the 35.45 plus the total amount of oxygen, 47.997, and we'll find that the potassium chlorate formula unit has a mass of about 122.5 atomic mass units. Now we have all of the information we need to determine what the relative composition of each element is. So the percent composition of potassium will be 39.098 atomic mass units of calcium divided by 122.5 atomic mass units of the total formula unit times 100%, results in about 31.9% of our compound being composed of potassium. For chlorine, we'll take the total amount of chlorine, 35.45 atomic mass units, divided by the total amount of the formula unit, 122.5 atomic mass units, multiplying by 100%, tells us that our compound is about 28.9% chlorine. We should be able to use that information and some subtraction to figure out how much oxygen it is, but we'll do it the straight way just to show. Oxygen is a 47.997 total atomic mass units out of our 122.5 total times 100% equals 39.2% of our compound. So potassium chlorate then is about 31.9% potassium, 28.9% chlorine, and 39.2% oxygen by mass. We have another question here. What is the percent composition by mass for each element in the compound sodium phosphate? I love a question like this because it forces us to incorporate a lot of our total knowledge of chemistry so far. Not only are we going to be practicing some of the percent composition that we've done so far in this presentation, but obviously also before we can even get to that part, we have to practice some of those nomenclature skills that we learned back in Module 3. So the first thing we got to do is we got to figure out what is the formula for sodium phosphate. And we know a good set of rules for determining our formulas. And that set of rules always starts with, is this an ionic compound or is this a covalent compound? And of course, we have a few things pointing us to the conclusion that this is an ionic compound. The first being that there's a metal there. We could look at the periodic table and identify sodium as a metal due to its position on that far left-hand side. The second, we could also see that it ends in ATE. Not only does that tell us that it's probably an ionic compound, it also furthermore tells us that the second constituent in that ionic compound is not just a single element, it is one of our polyatomic ions. And so to build that formula, I would follow that ionic set of rules, and I would be looking at a polyatomic ion chart to determine just what the heck phosphate is. I would then line up my charges and make sure that I had enough of each to balance out the positive and negative charges to form a neutral compound. When all of that is said and done, what I would find out is that we have sodium phosphate composed of sodium ions. Sodium always forms ions with a 1+ charge. And then I would look on my periodic table and I would see that phosphates are a polyatomic ion with the formula PO4. And phosphate always forms ions with a 3- charge. So I can see that the formula for that, I will need 3 of my sodium atoms to balance out all of that negative charge on the phosphate ions. So the formula is going to end up being Na3 PO4. And that's the formula for sodium phosphate, Na3PO4. So now I can go ahead with determining percent composition, and you may remember from the previous slide, if I'm going to determine percent composition using only a chemical formula, then I'm going to go by the atomic mass units of each element from the periodic table. And so I'm going to write those all down right quick. I see that I have sodium as one of my elements. And sodium has an atomic mass of 22.99. And I will also note that I have 3 sodiums in my compound. And I also will look at phosphorus. Phosphorus has an atomic mass of 30.974. There's only one of those in my compound. I'll put the 1 there to avoid any confusion. And then the final element I see is oxygen, and oxygen has an atomic mass of 15.999 AMU. There is 4 oxygens in our sodium phosphate formula unit, so we will multiply that by 4 to determine the total mass of our compound. We can see as we calculate those out that sodium has a total mass of 68.97 atomic mass units in our formula unit. Phosphorus will have the 30.974 atomic mass units in our compound, and oxygen, all 4 of the oxygens, will have a total of 64 atomic mass units in our compound total. Adding those all up together, shows me a total of about 163.9 total atomic mass units for 1 unit of sodium phosphate. And now I have quite enough information to determine the relative percent compositions. What I would do is take each compound, so the percent of sodium in our compound is 68.97 atomic mass units of sodium divided by 163.9 total atomic mass units in our compound. Multiply by 100. And see that I have about 42.1% of my compound being made of sodium. To determine percent composition of phosphorus, I will take 30.974 atomic mass units of phosphorus and divide by 163.9 total atomic mass units of phosphorus and multiply by 100. And I can see that my compound is about 18.9% phosphorus. And then finally, I will calculate oxygen's percent composition. There's 64 total grams of atomic mass units of oxygen in our compound, divided by about 163.9 atomic mass units total times 100%. And that's going to show me that oxygen is about 39% of my total compound's mass. Here we have another one where we need to utilize prior skills to determine what the formula for carbon dioxide is and then use that to determine a percent composition by mass. We hopefully can remember that this is probably a covalent compound because we see one of those words with the numerical prefix in front, specifically the dioxide, and we'll remember that when we're writing covalent compounds, we will simply use those numerical prefixes to guide us as to how many atoms of that element are present. Since carbon does not have a prefix, we can assume that there's only one carbon atom there, and the prefix di on oxide clues us into the fact that there would be 2 oxygen atoms there. So the formula for carbon dioxide, therefore, is CO2. And we've seen how we're going to use the atomic mass units, the atomic weights of each of these atoms from the periodic table to compare their masses to determine percent composition. Carbon has an atomic mass weight of 12.011 atomic mass units. Oxygen has an atomic weight of 15.999 atomic mass units. There is one carbon in carbon dioxide. There is two oxygens in carbon dioxide. The total amount of carbon is 12.011 atomic mass units. The total amount of oxygen is 31.998 atomic mass units. Adding them together, we can see that carbon dioxide has a total of 44.009 atomic mass units of mass in one molecule of carbon dioxide. If I want to know the relative percentages of that, we've seen how to do that so far. The relative percentage of carbon will be equal to the total amount of carbon, 12.011 atomic mass units, divided by the total amount of compound, 44.009 atomic mass units, multiplying that by 100%. In doing so, I find that about 27%, 27.3 to be specifically, about 27.3% of carbon dioxide is composed of carbon. The remaining percentage is oxygen. We could do a subtraction and figure that out. We're going to do it mathematically just for proof of concept. We see that 31.998 atomic mass units of our compound is oxygen. The compound has a total of 44.009 atomic mass units times 100%. And we can see that our molecule is composed of about 72.7% oxygen, which is what we expect by looking at the percentage of carbon there. So in conclusion, carbon dioxide is about 27.3% carbon by mass and 72.7% oxygen by mass. We've got one more of that same type. What is the percent composition by mass of each element in the compound phosphorus pentachloride? So we would need to ascertain that phosphorus pentachloride is also a covalent compound due to the fact that we do see one of those numerical prefixes in that compound name, specifically that penta designator, kind of clues us into the fact that there are numerical prefixes there, and so this will be a covalent style naming exercise or formula writing exercise. Phosphorus is not holding a numerical prefix, so therefore we can assume that there is only one phosphorus atom in our molecule. Penta makes us think of the word or the pentagon, maybe. Shape with 5 sides, so penta is correlated with the number 5, telling us that there are 5 chlorines in our molecule, giving us a total formula of PCl5. Then we're going to look at each atom's atomic mass to determine the relative percent composition. Phosphorus has an atomic mass of 30.974 atomic mass units. Chlorine has an atomic mass of 35.45 atomic mass units. There are 5 chlorine molecules there, while only one phosphorus atom is present. So if we take phosphorus, multiply it by 1, we can see that we have a total of 30.974. atomic mass units of phosphorus in our molecule. Multiplying the 35.45 times 5 atoms of chlorine tells us that there is 177.25 atomic mass units of chlorine in our molecule. If we add those numbers together, we see that in total the molecule has a mass of 208.2 atomic mass units. And then to figure out each individual constituent, the percentage of phosphorus will be 30.974 divided by 208.2 times 100%. And for chlorine, it will be 177.25 divided by 208.2 times 100%. For phosphorus, that gives us a result of 14.9%. And for chlorine, that gives us a result of 85.1%. Before we go any further, we need to stop and talk about something called empirical formulas. So percent composition alone cannot lead us to the actual overall chemical formula for a compound, but something we can determine from percent composition is what is known as the empirical formula. Empirical formulas tell us the lowest whole number ratio for elements in a compound. Empirical formulas are the most reduced form of a chemical formula. So for ionic compounds, their formulas are already empirical because they're already reduced down to their lowest ratios. However, for molecular compounds, because they're individual units, we don't always reduce them, but we can reduce them and call them the empirical formula instead of the chemical or molecular formula. I've given you some examples here below. The first one is glucose, again, the most simple sugar molecule we can identify, and glucose is formed of 6 carbon atoms, 12 oxygen atoms, and 6 oxygen atoms. So the chemical formula for glucose is C6H12O6. But each of those shares a common denominator of 6. So we can see that the ratio of carbon to hydrogen to oxygen is 1 to 2 to 1. So the empirical formula, if we divided each one by that common denominator 6, we would get that ratio in our empirical formula, CH2O. Another example is hydrogen peroxide. Hydrogen peroxide is made of 2 hydrogen atoms and 2 oxygen atoms. So the chemical formula, the actual structural formula of hydrogen peroxide is H2O2. But the empirical formula, the ratio of hydrogen atoms to oxygen atoms, is only 1 to 1 because 2 and 2 share the common denominator 2. If we want to write the empirical formula, we show that relationship by writing HO, which only would show 1 hydrogen and 1 oxygen, to denote that their ratio is 1 to 1 in their molecules. Okay, we are going to take a look here at how to turn some mass data into an empirical formula for an unknown compound. Our question here says a 170.00 gram sample of an identified compound contains 29.84 grams of sodium, 67.49 grams of chromium, and 72.67 grams of oxygen. What is the compound's empirical formula? So with this data, the first thing we can figure out is how many moles of each of these substances we have. So I'm going to do some mole conversions first. I would take the 29.84 grams of sodium, and I am going to set up a conversion using sodium's atomic mass that I retrieved from the periodic table. And I will see that sodium has an atomic mass of 22.9. So 1 mole of sodium is 22.99 grams. And so I can see that the conversion here tells me to divide 29.84 by 22.99. And that should give me somewhere around 1.30 moles of sodium. Then I will figure out how many moles of chromium I have. So we have 67.49 grams of chromium. And I'll set up a conversion. Look at the periodic table and see that 1 mole of chromium is 51.996 grams. And so I can see the conversion there says to do 67.49 divided by 51.996. And that also gives me about 1.3 moles of chromium. And then I will determine how much oxygen is in my sample in a molar quantity. I have 72.67 grams of oxygen. And I'll set that up in a conversion to try to figure out how many moles that is. 1 mole of oxygen is 15.999 grams. And I can see from the conversion there, I should divide 72.67 by 15.999 for a total of 4.5 moles of oxygen. So now we know from our sample that we have 1.3 moles of sodium, 1.3 moles of chromium, and 4.5 moles of oxygen. But empirical formulas give us molar quantities in the smallest whole number ratio. So to begin, I will find the smallest molar quantity among my constituent parts. And I see that both sodium and chromium have 1.3 moles. So I know that that's going to be the lowest amount of moles. So I'm going to divide all of the molar quantities by that smallest molar quantity. So I'll divide all of these by 1.3. So 1.3 divided by 1.3, 1.3 divided by 1.3. And in this case, for oxygen, it will be 4.5 divided by 1.3. And so that will tell us the whole number ratio, hopefully, of moles of each compound. If we divide 1.3 by 1.3, we get 1. If we divide 1.3 by 1.3, we get 1. And if we divide 4.5 by 1.3, the result is close to 3.5. So if we use these numbers, our empirical formula would look like this: Na, and we don't write a 1, Cr, and we don't write a 1, and O, 3.5. But we do not put decimals as subscripts in chemical formulas.
So again, we're trying to get to the lowest whole number ratio. So if I ever end up with decimals in these problems that aren't very close to a whole number, that can be rounded to a whole number, something like 0.5 here, I will need to multiply everything by some number that will give me a whole number. I can multiply 3.5 by 2 to give me a whole number, and so therefore I will multiply everything by 2 to give me whole numbers. And so the empirical formula for NaCrO 3.5 is actually Na2Cr2O7. All right, here in our next example, we read a 60-gram sample of tetraethyl lead, a gasoline additive, is found to contain 38.43 grams of lead, 17.83 grams of carbon, and 3.74 grams of hydrogen. Find its empirical formula. So we start this as we always do. We're going to determine the moles of each of our constituent elements. The first one we see is 38.43 grams of lead. We'll set up a conversion to moles. 1 mole of lead has a mass of 207.2 grams. And so when I divide 38.3 by 207.2, I get about 0.1855 moles of lead. Then 17.83 grams of carbon is our next constituent. We will convert that to moles as well. Carbon has a molecular weight of about 12.011 grams, so 1 mole weighs 12.011 grams. Dividing 17.83 by 12.011 gives us about 1.484 moles of carbon. And then we will figure out how many moles of hydrogen we have. 3.74 grams of hydrogen. Set up a mole conversion. 1 mole of hydrogen has a mass of about 1.008 grams. And 3.74 divided by 1.008 is about 3.710 moles of hydrogen. So now we have our exact amount of moles, and we want to convert them into relative ratios. So how many moles of lead versus how many moles of carbon versus how many moles of hydrogen, and we want those in whole number ratios. And the way we do that is we pick the smallest amount of moles and divide each of these parts by that smallest amount. So we're going to use the 0.1855 as that is the smallest amount of moles. And if we do 0.1855 divided by 0.1855, of course, we will get 1. Then we will do carbon, we will do 1.484 divided by 0.1855. And that is about 8. And then we will divide 3.71 by 0.1855. And that gives us a result of 20. So this compound, tetraethyl lead, has lead and carbon and hydrogen in a ratio of 1:8:20. And therefore, the empirical formula for tetraethyl lead would be Pb, with no number because there's only one, C8 to represent the 8 carbons, and H20 to represent the 20 hydrogens. Here we have our next example, which says 65.32 grams of some compound composed of sodium, oxygen, and sulfur contains 21.14 grams of sodium and 14.75 grams of sulfur. What is the empirical formula of this compound? Now we have to do a little bit of critical thinking for this problem, because we might notice right away that they don't give us the amount of oxygen. They only give us sodium and sulfur. And a lot of times that is the case. You have to infer how much oxygen is in a molecule, because when you're decomposing stuff to figure out what's in it, you are left with the solid sodium and sulfur by themselves on the benchtop that you can measure, but a lot of times the oxygen is lost to the air, so you just have to infer that the rest of it was oxygen. And so to determine how much oxygen we have, we'll take the total and minus the stuff we do know, and that should be what's left over should be oxygen. So if we have 65.32 grams total, and we subtract 21.14 of it because that is sodium, and 14.75 of the sodium, we should be left over with how much oxygen we have. So 5.32 minus 21.14 minus 14.75, we have 29.43 grams of oxygen. So now that we know how much oxygen we have, we can move forward with identifying how many moles of each substance we have. We'll start with oxygen since it's right there, 29.43 grams of oxygen. Set up the conversion. 1 mole of oxygen is about 15.999 grams. So when we divide 29.43 by 15.999, we see that we have 1.839 moles of oxygen. Next, we will determine moles of sodium. So we have 21.14 grams of sodium. Set up a conversion and say 1 mole of sodium is approximately 22.99 grams of sodium. And working that conversion through, 21.14 divided by 22.999 gives us about 0.9192 moles of sodium. And then working on the last one, we see 14.75 grams of sulfur. Set up a conversion. 1 mole of sulfur is equal to about 32.066 grams. And so our math there tells us to take 14.75 and divide it by 32.066. And we see that that is about 4600 moles of sulfur. So as we do, we will pick the smallest molar amount of all three, and then we will divide all three by that smallest molar amount to figure out whole number ratios for our constituents. So we will take each of these and divide them by 0.4600. And that comes up to about 4 moles of oxygen, about 2 moles of sodium, and of course 1 mole of sulfur. So the empirical formula for our compound here is O4 Na2S. So now we're going to tie what we just worked on back into the percent composition problems that we started with. Since percentage is just a scale from 0 to 100, when you are given the percent composition, you can convert these values directly to grams by assuming that you have a 100-gram sample. As an example, if you get a question that says an unknown sample of matter is analyzed for percent composition and it's found that the sample is 34.5% potassium and 65.5% bromine, you can just simply call that 34.5 grams of potassium and 65.5 grams of bromine by assuming that the whole sample weighs 100 grams. Then we can determine the empirical formula just like we just did by using those masses. So here we have our first example. A compound is 46.01% iron and 53.99% silicon by mass. And so we are going to calculate the empirical formula of this compound. So like we just talked about, we are just going to assume that this is a 100-gram sample of whatever substance is made of 46% iron and 53.99% silicon. By making that assumption, we can say within a 100-gram sample, we should have 46.01 grams of iron. And I'll go ahead and set up my conversions. And 53.99 grams of silicon. I'll go ahead and set up that conversion. You see that 1 mole of iron weighs about 55.847 grams. 1 mole of silicon has a mass of about 28.086 grams. So I will follow through with those conversions. 46.01 divided by 55.847. So I have approximately 0.8239 moles of iron in my 100-gram sample, and I would have about 1.92 moles of silicon in my 100-gram sample. Then when I do some so I will pick the lowest amount of moles and divide both. And I will do, so this will be 1, and then 1.99922 divided by 0.8239 gives me a result of about 2.0 333. So again, I can't write this formula. I'm done. I've figured out the ratio. I have one iron atom for every 2.3 essentially silicon atoms. And what I'll notice is I can't write a formula that looks like this, FeSi 2.333. I'm going to have to find something to multiply all of these by such that I get whole numbers, and I'm trying to keep it low. I'm trying to keep it reduced. I could try 2, and I would get a 2 for the iron, but I would only get a 4.66666666 for the silicon, so 2 will not work. If I tried 3, however, I would find that I would get 3 for the iron, so 1 times 3 is 3, and then 2.3333 times 3 would equal 7. And so that's going to be the lowest ratio of whole numbers I can depict for this compound. And so therefore the empirical formula for this compound would be Fe3Si7. Well, 7. That should be a 7 there. Here we have our next example. We can see that the compound contains oxygen at a percentage of 45.27. Well, excuse me, that's carbon, and then 9.499% hydrogen, and then 45.23% oxygen. When we do these problems, we can simply just assume that we have a 100-gram sample, and in the case of a 100-gram sample, we would have this many grams of each constituent. And so if we're going to set up our conversions, we would say we have 45.27 grams of carbon. We multiply that by the fact that 1 mole of carbon has a mass of about 12.011 grams. We see the division there tells us to do 45.27 by 12.011. That comes up to about 3.769 moles of carbon. Then I will do the hydrogen next. I see 9.499 grams of hydrogen. We'll multiply that by the conversion factor. 1 mole of hydrogen is about 1.008 grams. So I see I now need to divide 9.449 by 1.008 for about 9.374 moles of hydrogen. And then finally for the oxygen, it will be 45.23 grams of oxygen. Set up the conversion. 1 mole of oxygen is equal to about 15.999 grams. So now we will do 45.23 divided by 15.999. And we see that is about 2.827 moles of oxygen. Then we will find the smallest molar amount and divide all 3 by that smallest molar amount. So they will all 3 to be divided by the 2.827. And on the first one, 3.769 divided by 2.827. Is going to equal about 1.33. And then 9.374 divided by 2.827 is going to equal about 3.33, actually about 3.32. And then for the oxygen, it will just be 1, because 2.827 divided by 2.827 is 1. And we can see that we don't have whole numbers, so we need to find something to multiply all of them by so that we get whole numbers, and we're looking for the smallest number that we can do that with. I can tell you, now that we've seen one on the previous example, 2 won't work because 2 multiplied by those 0.3s will just end up in a 0.6. Anytime you see the 0.3333s in these problems, you should be thinking I'm probably going to multiply these by 3. And that will be the case here. We'll multiply the 1.3333 by 3 and arrive at about 4. We'll multiply the 3.3333 by 3 and arrive at about 10. And the 1 times 3, I'm going to put times 3 there so that you know what I did. The 1 times 3 will equal about 3. And so the empirical formula for our compound here is C4H10O3. This question is worded a little bit differently. It asks, if a fluoride of uranium contains 67.62% uranium by mass, what is its empirical formula? So we're asked to do a little bit of critical thinking here. We've got a compound and it says it's a fluoride of uranium. What that means is this compound is made of purely uranium and fluorine. We know how much uranium is in there, and we know it's 67.62% uranium. So the rest of it has to be fluorine. So fluorine would need to add up to 100. So to determine how much fluorine is in there, we're first going to take 100 and subtract the 67.62. So that means 32.38% of our compound is fluorine. Now that we have percentages, we can go ahead and assume the 100-gram sample and convert those percentages into grams. So I will start by setting up my uranium conversion, 67.62 grams of uranium. 1 mole of uranium has a mass of about 238.029. Uranium atoms are rather large. And when we divide that out, 67.62 divided by 238.029, we see that we have approximately 0.2841 moles of uranium in our compound, in our sample. And then for fluorine, that is an F, by the way. For fluorine, we will do 32.38 grams. Set up a conversion. 1 mole of fluorine is approximately 18.998 grams. We do 32.38 divided by 18.998. And we get about 1.704 moles of fluorine. Then we will divide both by the smallest molar amount, 0.281, 0.281. We will have 1 mole of uranium. And that comes up to about 6 moles of fluorine. And so the empirical formula for our compound is UF6. And that should be 2841s here. This problem is very much like the previous one. We can see that we have an oxide of chlorine containing 91.6% chlorine. That means the rest of it is going to be that oxygen to give us the oxide. So if I do 100 minus 91.6, I should see that my compound is approximately 91.6% chlorine, and the oxygen would be about 8.4%. So I can take those percentages, assume a 100 gram sample, and write them directly as grams. 8.4 grams of oxygen. Set up in my conversion, 1 mole of oxygen is about 15.999 grams. And I can see that that is about 0.5250 moles of oxygen. And then for chlorine, I will do 91.6 grams of chlorine, assuming a 100 gram sample. Set up a molar conversion, 1 mole of chlorine is about 35.453 grams. .6 divided by 35.453 is about 2.584 moles of chlorine. As I have already, I will divide both by the smallest molar amount, so 0.5250 and 0.5250. And we will see that this is 1 and this is approximately 5. And so the empirical formula for this compound would be OCl5. Now, we can take an empirical formula and convert it to the actual chemical formula if we are given the molecular mass of the whole compound. To do so, we will divide the molecular formula mass by the empirical formula mass. That result should give you a whole number. Then we will multiply each subscript in the empirical formula by that whole number to arrive at the chemical formula. We'll see a couple of examples on the next few slides. Our first example here says nicotine, an alkaloid in the nightshade family of plants that is mainly responsible for the addictive nature of cigarettes, contains 74.02% carbon, 8.710% hydrogen, and 17.27% nitrogen. If 40.57 grams of nicotine contains 0.250 moles of nicotine, what is the molecular formula? We have a lot to unpack here to determine what the molecular formula is of nicotine. We are given enough information to determine the empirical formula of nicotine given just the percent composition. Just like we have in our others, let's go ahead and assume that we have a 100 gram sample. Don't let this part, this 40.57, throw you off right now. We're going to use that to determine the overall molecular weight of the compound. What we're going to start with is just by determining the empirical formula using those percentages. So like we've already done, we're just going to assume that in a 100-gram sample, we would have 74.02 grams of carbon. We know that 1 mole of carbon has a mass of about 12.011 grams. Our conversion is set up now, and we can divide 74.02 by 12.011 to see that we would have about 6.16 moles of carbon in a 100-gram sample. For hydrogen, we would assume 8.71 grams in a 100-gram sample. And we know that 1 mole of hydrogen has a mass of about 1.008 grams. So dividing that through, we see that we would have about 8.64 moles of hydrogen in this sample. And then finally for nitrogen, we would assume 17.27 grams of nitrogen. Set up our conversion. 1 mole of nitrogen has a mass of about 14.007 grams. And we see that 17.27 divided by 14.007 is about 1.23 moles of nitrogen. We will divide each by that lowest molar amount, 1.23. And now we know the low whole number ratios of carbon to hydrogen to nitrogen for our formula. So we know the empirical formula. We can write the empirical formula C5H7N1. To find the empirical mass, we're going to add up each of the atomic masses that we see in that empirical formula. So we're going to add carbon 5 times, hydrogen 7 times, and nitrogen 1 time. That will look like this. Five times 12.011, because that's how much each carbon atom weighs, plus 7 times 1.008, because that's how much each hydrogen atom weighs. And then 1 times 14.007, because that is how much the nitrogen weighs. So our empirical formula has a formula mass of So we can see our empirical formula has a mass of about 81.113. We know that that is the reduced form of the molecular formula. We just don't know how many. We don't know what that common divisor was. We don't know how many it's been divided by to give us the empirical formula. But we do know we have enough information in this problem. In fact, we have it. This amount of grams is this many moles of nicotine. So we can use these numbers to figure out what the molecular weight of nicotine is. We know that we have 40.57 grams. We know that we have 0.25 moles. And so we know molecular weight is grams per mole. So if we divide 40.57 by 0.25, we'll have the molecular weight. So this will look like this. 40.57 grams divided by 0.25 moles will equal 162.28 grams per mole. So what we've essentially done is said that our empirical formula shows a weight of 81.113. The actual weight of nicotine is 162.28. So to figure out how many times it was reduced by, we will divide the actual molecular weight by the empirical formula molecular weight. So 162.28 divided by 81.113. When you do that in your calculator, you should see that this result is pretty much 2. So we will do 162.28 divided by 81.113 equals 2. So what that means is everything in our empirical formula has been reduced by 2, or everything in our molecular formula has been reduced by 2 to get to the empirical formula. So to get back to the molecular formula, we just multiply everything by 2, meaning that the chemical formula for nicotine will be C10, because 5 times 2 is 10, H14, because 7 times 2 is 14, and N2, because 2 times 1 is 2. So that's how we take the empirical formula and arrive at the molecular formula. We have to have the molecular weight to do so, or a way of finding out the molecular weight like we did in this problem. We have another example here, perhaps easier. They've given us the molecular mass in this one, and so all we need to do is start by just determining the empirical formula of the compound that we are asked about. We can then use that empirical formula to figure out what the molecular formula is. To determine what the empirical formula is, we start by assuming that we have a 100-gram sample with which we can convert these percentages into grams. So to determine the moles of phosphorus, I'm going to take 27.6 grams of phosphorus, set up my conversion. 1 mole of phosphorus has a mass of about 30.974 grams. Doing that, 27.6 divided by 30.974 tells me that I have about 0.8911 grams. Oh, excuse me, not grams, moles of phosphorus. Then for nitrogen, I will take the 12.1% and convert it to grams of nitrogen by assuming that I have a 100-gram sample. 1 mole of nitrogen has a mass of about 14.007 grams. Calculating that through, 12.1 divided by 14.007 means that I have about 0.863 moles of nitrogen. And then for chlorine, we see a 61.2%, so we will convert that to grams. 1 mole of chlorine has a mass of about 35.453 grams. Once we divide 61.2 by 35.453, we see that we have about 1.73 moles of chlorine. Again, I will divide each of these by the smallest molar amount. So I will divide 0.863, 0.863, 0.863. I will see this first one is approximately 1, the second one is approximately 1, and then the third one is approximately 2. So the empirical formula would be PnCl2. We're going to calculate what the empirical formula mass would be, and we would do that by adding all of the atomic masses in that empirical formula. So 1 phosphorus is 30.974, plus 1 nitrogen is 14.007, plus 2 chlorines was 2 times 35.453. So the formula weight for our empirical formula is about 115.9. About 115.9. The weight of our molecular formula is 695. So to figure out how many times our empirical formula has been reduced by, we're going to divide that 695 by the 115.9. And we see that that is a result of about 6. So our empirical formula has been reduced using the common denominator 6. We're going to multiply everything in those subscripts by 6 to arrive at the molecular formula, meaning that the molecular formula for this compound is P6N6Cl12.